last portion of 9.3. So if you look in your book, we're on page 597, where it says power of a test. So the power of a test. If you flip the page, there is a green box definition there. The power of the test is the probability that the test will find convincing evidence for the ha when a specific alternative value of the parameter is true. Okay, so if a specific, the other one is true, you actually do want to find evidence for the ha, right? Okay, so the power of the test is how strong is the test? Because if you are, the ha is true, and you for some reason do not find convincing evidence, and you fail to reject the ho when you're supposed to reject the ho, what kind of error is that? Is it a type 1 or a type 2 error? That'd be a type 2 error, right? So the power of the test is, so the stronger the power of the test, the less likely you will have a type 2 error, okay? All right. So think of it that way. Think of a power of a test in that sense. Okay, as a matter of fact, if you go to page 599, there is the relationship between the power and the type 2 error. In other words, the power of the test, so the power of the test plus the type 2 error probability is 1. So the stronger the power, the less likely you will have a type 2 error. The weaker the power of the test, more likely you will have a type 2 error, okay? So obviously you want the test to be powerful. In other words, when the ha is true, when you're supposed to fail to reject the ho, you want to fail to reject the ho, okay? All right? So that's the power of the test, okay? So if you go to example on page 598, it says, can we tell if the new batteries last longer? Let's return to one last time to the company that developed a new deluxe AAA battery that is supposed to last longer than its regular AAA battery. Based on years of experience, the company's regular AAA batteries last for 30 hours. The company plans to select an SRS of 50 deluxe AAA batteries and use them continuously until they completely drain. Then it'll perform the test where the ha is that the mu is greater than 30, right? The ho would be, because the ho is going to be, what we're trying to disprove is going to be this. What we want to happen is this, and we're going to use an alpha of 0.05. Okay, so we're going to do a significance testing doing this, where mu is the true mean lifetime in hours of the deluxe AAA batteries. Okay, blah, blah, blah. The power of the test to detect that mu is equal to 31 is 0.762. So interpret this value. So the power of the test was 0.762. Okay, so it means that if you interpret this, it means that if the true mean value of the company's AAA batteries is 31, there is this probability that you will actually find convincing evidence for this. Okay, in other words, it'll come out the way you want it to come out. Right? The power is 0.762. Or you can say that you don't want to say this. Whenever they ask you to interpret it, you just do what I said. But the flip side is that the type 2 error is going to be 0.238. So that's a significant amount of error or significant chance of error. That is like 1 out of 4. 1 out of 4 times you will come up with a type 2 error. Okay, so this is really not a powerful test. Okay. All right, so let's go ahead and do the powerful batteries. Let's look at the powerful batteries. And this is the part that I really wanted you guys to pay attention to. And this is why we were actually going to pull this section apart and do it separately and dedicate a full class to this. Okay. So let's say that in this battery experiment, we're going to have so this is going to be the hole. This is going to be the hole where mu is going to be equal to 30. Okay. The ha is it's actually 31. Right, so you're going to have a distribution that looks like this. Okay. So when I do a test, right, I'm going to have something that looks like this. I'm going to have something that looks like this. Okay. So let's look at the ha first. Okay. Let's get the ha first. In the ha, everything from here on out is going to be your power of the test, because you actually have found that there is convincing evidence for the ha, all right, and you were going to reject the ho. So here, this here is going to be the power of the test. Okay. So based upon what we just heard, what we just said, we can also say that this guy here is going to be what? This is the 1 minus the power of the test. So this is obviously going to be your type 2 error. Okay. So on the ho, okay, if you find something over here, you're going to accept the ho. You're going to fail to reject the ho, right? You're going to fail to reject the ho, right? And which is what you're supposed to do. But in this section up here, you will not. So this is your type 1 error, okay? So remember this, okay? So the type 2 error is the tail over here. The type 1 error is the error over here. Okay, you're using 2 different distributions here, right? This is where mu is equal to 30. This is mu is equal to 31. Okay, so what are the things that I can do to reduce the type 1 error, or for that matter, the type 1 error, these errors, right? If I had my mu was actually 33, and I shifted it over here, what's that going to do to the type 2 error? Is that going to reduce it, or is it going to increase it? If I shifted this over here, it's going to reduce it, right? Because the tail over here is going to be less, right? So the greater the separation between these two, I'm going to have less of a type 2 error. The power of my test is going to be bigger. Okay, so if the difference in these two are large, if they're separated apart, I'm going to have less of an error. What happens if on these sampling distributions, if I used an n that is greater than what I have here? What will that do to the graph? What happens, what parameter or statistic changes as the sample size changes? Is there something that changes? Right? So as n goes up, your standard deviation of both of these is going to get smaller and smaller. In other words, both of these graphs are going to become more attenuated, okay, which means that you will have less on the tails, okay, on either side, right? Because it's going to become more sharper. It's going to be more sharper like this, which means, again, if you leave this the same, your type 2 error will become smaller, and your type 1 error will become smaller too, okay? So the power of the test, since the type 2 error becomes smaller, the power of your test became greater. Okay, so we've talked about two different things here that can change the power of the test. The first thing is actually the 31 and 32, I mean the 30 and the 31, this gap becoming larger, okay, obviously makes the power of the test bigger. Okay, so in other words, so what does that mean? That means that if the difference between the truth, the ho and the ha become larger, it becomes easier to detect, right? We have less errors. That only makes sense, right? Okay. Again, so that's first, that's number one. And then the second one is that the more samples you draw, right, the more accurate, so that you're going to have less of a type 2 error, less of a type 1 error, because this one also gets squished up, meaning that the tails are going to become smaller and smaller. Okay, so those are the two. And then there's one last one, and that one is, if you go flip the page, where are they? We're on actually page 601. Okay, the significance level alpha is larger. If the significance level alpha is larger, what does that mean? What was alpha? Alpha was the same as a type 1 error, right? So if the alpha becomes larger, your type 1 error will become larger because you're going to shift this guy over here. You're going to shift it over here, which means that as you shift it over here, you're going to get less of a type 2 error, okay? The power of the test becomes greater. Okay, so if you go to page 601, it says 3 ways. There's a green box there that says increasing the power of a significance test. 3 things you can do. So it says the power of a significance test to detect an alternative value of the parameter when the ho is false and the ha is true, based on a random sample size n and the significance level alpha, will be larger. The power of the test will be larger when, okay, the n becomes larger because you're attenuating them, all right? It becomes sharper up here, so you have less tails. So the type 2 error becomes smaller, the power of the test becomes larger. Okay, that was one. And that one is the first one. The second one is the significance level alpha is larger. So if the significance level alpha is larger, you're gonna push this over here, which means that you push this guy over here. Type 2 level, type 2 error becomes smaller. Consequently, the power of the test becomes larger. Okay. The third one, if the null, the ho and the ha values are further apart. Again, if this is further apart, it's going to be easier to detect, and you're going to have less of type 2 error, right? Okay. All right, so that's that. Let's go ahead and kind of look at the example there on page 602. The researchers in the Alzheimer's experiment want to test the drug manufacturer's claim that fewer than 10% of the patients who take its new drug for testing or for treating Alzheimer's will experience nausea. That is, they want to carry out a test that the ho where p is equal to 0.1, the ha is p is equal to less than 0.1. Okay, notice we're talking about not mean now, we're talking about probability, we're talking about proportions here, right? Where p is the true proportion of patients like the ones in the study who would experience nausea when taking the new Alzheimer's drug. Earlier, we mentioned that the power of the test was to detect P is equal to 0.08 using a random sample of 300, and significance level of 0.05 is 0.29. Because the power of the test is 0.29, okay? Determine whether each of the following changes would increase or decrease the power of the test. So if we use an alpha level of 0.01 versus 0.05, okay, so you're gonna shift this guy from here to here, right? Because now we're gonna have less of an alpha, right? So your power of the test becomes smaller, correct? It decreases. B, if the true proportion of P is 0.06 instead of 0.08. So 0.06, 0.08. So actually, okay, this is different, right? Because, wait. So now here we're gonna have a larger difference, which means that it's gonna be easier to detect, which means that the power is gonna increase, okay? Now on the third one, N is equal to 200 instead of 300. So if we use less of a sample size, it becomes less attenuated, which means that the power of the test becomes smaller, okay? All right. So that's that. Where are we at? So let's go ahead and go at 603. It says using tests wisely. And there are two things there. One is the statistical significance and practical importance. Okay, the other one is beware of multiple analyses. Okay. So these are things that you're probably not going to be tested in the AP test, but there are kind of good things to know. Okay. Statistical significance and practical importance. Okay. So if you do a test, let's say that, okay, let's go ahead and let's use the example of the book. Let's see what the book says. Suppose we are testing a new antibacterial cream, formulation NS, on a small cut made on the inner forearm. So if we are going to, we know that from previous research that the small cut, that the, without no medication, the healing time is 7.6 days, okay? So if we do a significance testing where the mean time is 7.6 with no medication, but if we use the medication and we're gonna do a test where let's say that it is less than that, and it turns out that, well, it's less, but it's less by a day difference. Okay, so the practical importance that comes in here is that why even do the test if you're talking about a medication that's, if you use, is going to make it scab over at 7.6 days versus if you use it, it's going to scab over at 6.6 days. So how are you going to advertise this drug? Oh, we did testing, and if you use it on a daily basis, if you go ahead and put it on for a day, for every day for 7 days, it's not going to take you 7.6 days, but it's going to take you 6.6 days. Now, is this something you're going to buy? No, I'm not going to buy it. I'm not going to buy something and put it on every day just so it can give, it'll go away one day more. So the practical importance there's a practicality there, right? So what's the whole point in doing it? Okay. Now, if you were a doctor or something like that, and you found a cure for something that will cure like an ACL injury in 6 weeks versus 9 weeks, you have a market there, right? Because many athletes are going to buy that to get back to whatever they want their sport 3 weeks earlier. Okay, so there's a difference there, but you always have to think before you do these tests, why am I doing these tests in the first place? Does it make sense to do the test? Okay, so that's what they're talking about there. The second one, beware of multiple analyses. Okay, this one is, okay, I'm going to let you guys read this. This is something that's kind of out there. All right, something that you guys are not going to have to deal with, but it's really called, it's called a data dredging or p-hacking. In other words, you can manipulate data to change the p-value and change your test, okay, by keep on doing the test over and over and over again until you get your desired p-value. Okay? Not a good thing to do, okay? Again, you're manipulating data there, okay? All right? So that's that. So we have finished 9.3.